And start whenever we tell us that we can do it.
Yes, so I'm ready.
Well, yeah, so sure, let's then get started.
Okay. So should I just start? I
Yes, please.
introduce
Yeah.
myself? Okay,
Yes.
great. Well, thanks a lot to you and other organizers for giving me this opportunity. I'm very excited to talk to you about deep learning with Bayesian principles. I hope that you can see my mouse. This cursor is good. Okay. Should
We can see it,
also,
yes.
okay, and I need to disable the annotation. Okay, I've done this. So, and the voice is clear. I guess if anybody has any problem, please feel free to write in the chat window. And if there is any other issue, please bring it to our attention as soon as you can. Okay, so my name is Mohammed EMTIYAZ Khan, and you can just call me MT. And I work at RIKEN Center for AI Project in Tokyo. And before I start, I would like to thank the two key people who have helped me to prepare this presentation. Roman Bachman, who used to be an intern with me, he's originally from EPFL, and Xiangming Meng, who was a postdoc at RIKEN AIP in our team. Um, so uh, I will uh, I will be talking about deep learning with Bayesian principle, and the goal of this tutorial is to bring the two communities of deep learning researchers and Bayesian researchers together, and to show that they're not that different, and there is lots of things that are common between them, and that you can benefit from putting these two ideas together. Okay. And my interest in this field comes, from my own research. So let me start with that. So, like many machine learning researchers, my goal is to discover fundamental principles of learning from data and use these principles to develop algorithms that can learn like living beings, like humans and animals. And I just want to share with you today how deep learning and Bayesian learning sort of help to put these put to me to achieve my own goal in my research. And Just to give you an idea of what I mean by learning like living beings, I would like to show you this video of my daughter who is, when she was very young, she was trying to learn about the world, and right now she is focused on the ukulele and the bed, and she's kind of figuring out slowly over time. I hope you can see the video. She's slowly figuring out over time what kind of things she likes in the world. So she's figuring out that the sheets are not that important, and anywhere the sound doesn't come from doesn't really excite her. And she's building these preferences about the world. So when I say learning like living beings, humans, animals, this is what I'm talking about, that we are sort of collecting experiences about the world and slowly figuring out which experiences do we like and which experiences are not that important for us. And we don't really stop at this step. We continue to learn in the world, and this is like 6 months after that. So when she was 1 year old, she has sort of converged into figuring out that the fretboard where the sound comes from is the interesting part for her, and everything else is irrelevant. So it's really amazing how we learn in the world, trying to figure out what our preferences are and trying to discard everything else that's not that important to us. And we don't stop there. We continue with this learning to transfer our knowledge to new novel setting. We can adapt what we know before to a new environment. Like in this case, she doesn't have a ukulele, but now she has a guitar, and guitar is a much bigger instrument. but the basic principle behind this is the same as the sound comes from the fretboard. And she is now going towards the experiences that she really likes in the world, which is the sound, and she has somehow adapted her skills to play the guitar. I mean, you can't really say that it's playing the guitar, but she's able to still get the data that she wants. So this is what fascinates me, and I call this like learning of living being, and here I have named it as human learning. But what my point is that this kind of learning that we see around in, organisms, in animals and humans, and all sorts of things around us, this learning is of lifelong nature. So it just continues to happen throughout the life of the agent. But it happens in small chunks. So you sit in a room. When you're a baby, you were just you could see only 2 meters away from where you are, and still you're learning from there. And then when you grow up, you can walk around, and you're able to learn sitting in a room like right now attending this lecture. Even you're seeing data in small chunks, you're able to learn from it. And even if the world changes around you, so if the world kind of, you go to a different lecture and the person's talking about a different thing, you still will be able to absorb that information. So this characteristics of, learning of living being, it's of this lifelong nature, happens in very small chunks of information, and it is very adaptive and can go into non-stationary setting. And if we contrast this type of learning to the learning of the machine that we have, the best kind, which is, for example, deep learning, the setting is very different. Here we assume that everything, all the data, it's available in bulk, and everything that we want to know in the world is available in this large amount of data, in this data that comes from a stationary world that doesn't change. So the number of classes are not going to change. The objects that I'm going to learn about are all present in this ImageNet data set. Right? So these two types of learning are very, very different. And I'm not saying one is better than the other, but they have different characteristics for now. And my interest has been into putting these two types of learning and at one place, trying to bring them closer together. So that's what I and the group that I belong to, we focus on. And when I think about a mathematical framework that can explain how human learning happens, how learning of living being happens, I turn to Bayesian learning. So there has been a lot of work, and I have put some of this here, and there's lots and lots of work in psychology, in neuroscience and economics, where people argue that the kind of learning that we do as humans or agents in the world, it has to follow some sort of Bayesian principle. So the updating sort of happens sequentially. Whenever you see a new observation, you're able to incorporate it into your belief, which is like a posterior distribution. And so that's how I sort of come towards, putting the area of deep learning and the Bayesian learning together. Because human learning can be explained in some sense by a Bayesian type of learning. Okay, so what I want to share with you is that what I've learned looking into Bayesian learning and deep learning, and of course, as many of you might realize, that these two are not quite the same. They look very, very different. I mean, it's very, very different, and the kind of models that we used in deep learning versus Bayesian models, they're very different, right? So Bayesian models, if you have heard of some of them, is Bayesian networks, probabilistic graphical models, or Gaussian processes. But in deep learning, these are more black box models, so you don't like go there and design every part of the model, but rather it's like just have lots of layers and a neural network of different kind with different architecture, right? So there's not going inside and designing every bit of it, but rather it's a more black box. In sense of learning, the type of algorithms that we would use for deep learning, which is mostly stochastic training, versus Bayesian inference, which is based on this Bayes rule, they're also fundamentally different. Right? And because of these fundamental differences, the advantages and disadvantages, like pros and cons of the two approaches, are also very different. So Bayesian approaches, they uh, they don't really work very well with large data and large model, and they don't scale very well. Their training is very complicated, while deep learning, it works amazingly well. But on the other hand, and this I will discuss very soon, is that deep learning models are very confident. They only pay attention to the data in hand, and they don't look outside the data. Like what my daughter was doing in that video, is that she's trying to figure out what she likes and what she doesn't. And this type of property is more present in Bayesian learning, that you are able to somehow quantify what you know, which is in the data, and what you don't know, which is outside the data. Okay? And because of this property, you're able to fill this gap in the knowledge, that when you see something new in the world, you're able to incorporate it and say, oh, I didn't know this before, and now I'm going to put this knowledge here. But this kind of stuff doesn't happen in deep learning, and the algorithms that we use are not, models and algorithms that we use are not able to handle this. So they are, my point here is that they are very different kind of learning, and that's why I'm now talking in this tutorial about how can we see the two types of learning to be the same. Right? So bringing these two together to combine their strengths and try to use those strengths to solve a challenging learning problem. And I will focus on lifelong learning, like the kind of thing that I showed before, by putting these two ideas together. So that's the topic of the tutorial. Deep learning with Bayesian principle. What I will actually do is that I will present a set of Bayesian principles, and they're not like, so Bayesian learning is one type of thing, but then there's Bayesian principle, there's some other things around it, and I'm going to use those fundamental principles to show that the two kind of learning is actually not very different. They can all be explained with the same set of principles. So that'll be the first part. To design, to improve, and generalize existing learning algorithms using the same set of principles that are Bayesian principle. And what we will see there is that everything boils down to starting with a Bayesian problem, looking at the posterior distribution, and then seeking approximation to the posterior. And once we do approximation, it turns out that we start seeing many different types of algorithms out of it. So we will look into deep learning algorithms like SGD, RMSProp, Adam, Newton method, and all this other things in optimization. And then we'll touch upon how this relates to more classical Bayesian stuff and some approximation algorithms that people talk about. And all of these are covered within the same set of principles. Now, once we are able to put everything at the same platform, then in the next part, we will see how we can use this idea of everything being the same to design and improve existing algorithms. So we'll focus on deep learning algorithm. We'll talk about uncertainty estimation. Then we'll see how we can extend existing methods for deep learning to do lifelong learning. Okay, I'm not sure if I'll have time to cover all of this, and it's possible that we'll just do a very quick of this, but the main point of the tutorial will be here. Hopefully, if we have time, we can also cover this in detail. So just remember, in the end, what you will see here is that everything to bring together with one set of principles. Okay? And everything is the same, so that we can talk and we borrow strength from different communities. Okay. So I call the tutorials Deep Learning from Bayesian Principles. And there are also other speakers here who are going to talk about Bayesian and deep learning stuff. I think maybe Andrew talked about it already yesterday. And you might ask, how is this different from Bayesian deep learning? And so in Bayesian deep learning, people are using Bayesian ideas to improve deep learning, or deep learning ideas to improve Bayesian learning. My focus here goes a little bit more into the big picture rather than in the details, is that I want to focus on the principle of how you can see everything being the same. And that then allows you to, maybe look into these efforts of borrowing, strengths from each area and help enhance our the existing Bayesian deep learning research. So my audience, as I said, is deep learning and Bayesian principle, and to bring it together is the goal. But the tutorial is not really about the details of um, individual methods. So we're not going to go into Bayesian deep learning methods or like Bayesian inference methods. So this tutorial will not cover the details of these individual things that you might have heard. It will not make you an expert on Bayesian learning, or it will not make you an expert on deep learning, or it will not make you an expert in Bayesian deep learning. But it'll give you an understanding of how, at the big picture level, things fit together, and it'll help you to maybe in your research when you sit down and do the details using any of these specific things. So there are lots of amazing things here, but I will not go into it. Okay. So the other thing that I say that I might not really have time to discuss many things, many important and relevant works, and lots of things happen. Things come in archive all the time, and I really am not able to keep track of lots of amazing things that are happening. And if you really think that there's something important that I should include, please send me an email and I'll try to do it better. In last like 6 months since I gave the Neurips tutorial, nobody's emailed me yet. So I think I'm doing okay so far. But if you, I'm really looking forward to improvements. If you have any ideas, please feel free to send me an email. And also, the content of the tutorial is really biased. It's just some things that I've been looking into for the last like 10 years or so. And so a lot of it is just based on what I see how things are. A lot of it is just kind of my own work, but I'm not trying to advertise my work. But this is just my perspective in the problem of how I see, and I think this is an important perspective, and that's why I'm talking about this. So I hope that it doesn't offend other people, and if it does, please feel free to send me an email, and I'll be very happy to talk to you about it. Okay, so with that, we've covered the first part. Are there any questions that we should be taking at this point? Okay, where should I look for questions?
No, we can just continue if there is nothing. We cannot just discuss anything specific.
Okay, great. All right, so I'll get into the first main part, which is about trying to first understand the basics of deep learning and Bayesian learning, how they're really different from each other, and what are their pros and cons. So let's get into that. Let's start with deep learning, and this probably most of you are familiar with. It's based on this frequentist idea of minimizing some kind of risk or loss, or maximizing some kind of likelihood. And this is basically coming from the principle of trial and error, that if you're given some data and you have a model with some parameters, then you want to fit the model, and then you want to check how well you do to fit the to predict the data points, and you look into this loss, and this loss might be defined using something like ERM or maximum likelihood. Then you try to minimize this loss. So to give you an example, you may think of supervised learning problem. where xi is the input, f is probably a neural network or a model with some parameter theta, and then you try to predict the output. So it might be x is some kind of image, and y is some kind of like depth in that of the pixel in that image, and you're trying to predict that depth, which is this yi, and you have the truth, and you try to minimize the square between your prediction and the truth. You sum it over your whole data set. You add a small regularizer because you don't want to overfit. Okay, so this is a very, very standard thing in deep learning. And the type of algorithms that you use to minimize this, they mostly look like this, where you are updating the parameter by computing the gradient of this loss. So this gradient could be stochastic gradient computed over a mini batch, but then you precondition it using some kind of preconditioning matrix or vector, like in these algorithms like RMS-prop and Adam and Newton's method, and you update things. And this is a very, very simple algorithm. And this simple choice of the algorithm and the loss and the framework allows you to scale to very large data sets and very complex models. So it's very, very simple, and that's really works really great in practice. But then there's some problems that we don't usually talk about, and what I'm going to do is I'm going to show that this kind of approach actually works quite well, but then there are serious issues with this approaches, and that's where then Bayesian learning comes in. Okay, so I'm going to first talk about the problem, and I want you to think a little bit about the problem by yourself first, and for that I show you this data set. Here each this diamond is a data point, and you see that the and y-axis is some kind of frequency. So it's telling you something like, once in a year, 10 times a year, 100 times a year, maybe once in 100 years, once in 10 years, once in 100 years, something like that. And what the data is showing is that as you go along the x-axis, which is linear, your frequency of the event is going down. Okay. And now I'm asking a question of like, how should I fit the data? And I give you the choice of two fit. Okay, so there's one line. This is the blue line. You could fit it with a straight line, or you could fit it with two straight lines. So there's this red line is like you have one line here and then another line. The slope sort of changes a little bit. And the question that I'm asking you is, which is a good fit? Oh my God, I messed it up. Okay, that's a bad idea. So I want to do a quiz of what you think is a better fit. Rodrigo, can we do that right now, the quiz?
Yes, of course, we can ask the audience.
Okay. So I guess there is a mechanism for you to vote on the poll.
Well, people are writing on the chat window, and most of them are voting for red.
Okay, good. Okay, I messed up a little bit, but it's not important what answer you get, and there is no clear answer here. But I want you to think, and that's why I'm asking this question. And is there more answer coming, or should I just now continue with the?
You can continue.
Okay, great. So I guess most of you are going for red, but again, there's no good answer here. So what happens is actually this is the result, not from you, but this is from a few years ago from my lecture in EPFL, where there were 200 students and all beginners in machine learning, and usually people kind of are not really able to tell which model should be used. It's almost like kind of 50-50. And you see that there is also a little bit more inclination towards red. And this is a fair answer because it's very hard to tell which model you should be using. but it's because I have not given you, I've sort of cheated a little bit and I've not given you the full clue. So there's one piece of information that I could give you is that the x-axis is actually magnitude of earthquake. Okay, so this is a real data. It's taken from this excellent book, and I really encourage you to read it if you want to know more about this this example. It's from this book, The Signal and the Noise. And now what it's actually telling you is that the x-axis is the magnitude of earthquake, so it's increasing. And this is like large earthquake, and this is like smaller earthquakes, okay? And so what it's actually telling you is that as you go, towards high, large earthquakes, their frequency goes down, which makes sense because, thank God that large earthquakes don't happen all the time. They happen very rarely. But the small earthquakes are very happening very often. So now with this piece of information, I want you to think again and then answer the question, which is a better fit? Is it the red line or the blue line? Okay, so can we do another poll on this? So I'm asking you again the same question with this new piece of information that the x-axis is the magnitude of earthquake, and I want you to think if your opinion has changed now. So how does the result look like? Rodrigo?
Oops, no.
Do we have
there is no question, sorry. Yeah.
Sorry, there's no question?
No, sorry.
Okay. Okay, maybe then it's fine. So we'll skip the it's fine. I hope that you have thought in your head if your opinion has changed or not, but I'm going to sort of give you the answer now, okay? So the quiz was supposed to be twice. It's before I give you this piece of information and after I, afterwards telling you that this is earthquake. Okay, so the key point here with this piece of information that the x-axis is earthquake is to realize that that you have a lot of data here and you have very little data here. Okay, so when you're talking about earthquakes, the large earthquakes happen less often, so you have very little data here, and small earthquakes happen more often, so you have lots of data here. So you actually know with lots of confidence here that the line should be pretty much here. But as you go towards the high magnitude earthquake, you have less and less idea. Okay, so the real situation, maybe I should. The real situation is actually that you don't know that much here, right? But the important thing is that you actually want to know your decision matters in this side. Your decision doesn't matter here, meaning that you don't really care about small earthquakes because they don't do much damage. But you really care what happens here, but you have less data there. So I hope you see the consequences of having less data. And if you choose the red line, then you're actually taking more risk. Why? It's because if you look at the prediction that are made for high earthquakes, so consider this 8.5 earthquake, this happened in Japan in 2011. This red line suggests that it's gonna happen once in 1,000 years. While the blue line is suggesting that this earthquake is gonna happen once in 100 years. So the blue line is more conservative. It's saying that the large earthquakes can happen more often. That means that we should be more careful that it could happen in our lifetime. We should design our building to be more conservative, right? So the issue is that in deep learning type of methods, you're only resorting to one model, one theta, and you have to make a choice, the kind of choice that I gave you, red or blue. And if you don't know enough about your data or the problem, you might actually make a wrong choice. And if you make a wrong choice, if you pick the red model, then you're going to put many people's life in danger. Okay. So I hope that that makes sense to you. And what I want to say is that what you ideally want to do is to also have a degree of confidence in your prediction, meaning that you reflect the fact that there's more data here, so you're very confident here, but here you don't really know what's going on. Okay, so you can't really tell apart between blue and red. And maybe you want to go more conservative in this point. So you want to push the math on that side. So you want to look into the tail of your, probability. So this is like this confidence interval, and you want to like minimize the mass that you put. So your model should be more and more conservative. So maybe you want to pick a line that goes somewhere here. Okay, so the point is that you want to acknowledge that what the model does not know, and you want to choose a less risky option. Okay, and okay. You might actually think that this kind of example doesn't really happen in machine learning, and this is a very classical statistics example. But then I would want you to think a little bit more. In many classification problems, many deep learning problems, this actually happens, but we don't realize it until we deploy our model and we actually see the failure. So for example, you can take ImageNet data, and it's possible that for some classes you have lots of data. So maybe the data was recorded in a North American country where people look differently than people in Asia and Africa. And then you have lots of data about those people, but then when you want to deploy those technologies to those other countries where you have not collected the data, then you will have this bias. And this is already having a lot of issues in the real world that we are actually facing. So this is a very, very important point. And this is a drawback that we have in our current deep learning methods. So I hope that that convinces you that this is important. And now what I want to do is I want to show you how Bayesian methods actually fix this problem. Okay, so I'm going to just illustrate it rather than giving you equations. Actually, let me move this slightly here. Okay, all right, good. So I just want to show you on this example how Bayesian method would work. So the key idea of a Bayesian method or Bayesian principle is to not pay attention to one model, rather try to look into a range of possibilities. So use a prior distribution or some other distribution, just some uniform distribution or some any other distribution to sample a lot of candidate choices. So what that looks like is that you have sampled maybe many different lines. Some of them are linear, some one line, some of them have two pieces, some of them have three pieces, and this range of models that can explain your data. Then you look into your likelihood. So this could be like squared error loss that you had. So in that case, this will be a Gaussian. So you have this likelihood. What you do is you take this theta, so this line, and you evaluate it on each data point. You try to see if it explains the output well, and that gives you a weight. So it's like a scoring through the likelihood or the loss. You score each model. Okay, so this is for all data. You get this for each theta, and this will sort of give you a weight on each line. Okay, so what it's actually telling you is that this middle line is the most appropriate one. But as you move away from it, your model doesn't really explain the data very well. So the weight becomes smaller and smaller. And then what you want to understand is like you go at what point this becomes less relevant. So at what point you need to stop looking at these lines. So what is the confidence interval? Okay, is it very narrow or is it very broad? Okay, and for that, what we do is we use this Bayes rule. Is that we take this top score, so it's like this probability times this probability, is the width of this line, and then you put it at the top, and then you normalize. So you look at all possible weights. So you look at all models that you have, you look at their weights, you sum them up, and then you normalize this probability with this weight. Okay, and if you do this, then this sort of gives you this range. It tells you that, oh, you need to cut the model here. This is like maybe your 95% interval, like 95% of the mass should fall within these lines, and then everything outside does not really matter. So you should look into the models that are inside. Okay, so the main idea here is that then you get this kind of this uncertainty around it, and the way that you get it is by looking into all possible explanation of your data in hand, not just looking at one theta, rather than that, like looking at a wide range of possibilities, and these possibilities are sampled from a prior distribution. Okay, so you can see the problem that the difficulty of this procedure is to compute this integral, right? Because you're looking into all possible explanation of your data, and there might be just infinitely many models that can explain your data. Some are good, some are really, really bad, right? But you don't know where to stop. And to figure out this range of which models are reasonable and which models are terrible, you need to compute this integral and normalize the thing. And you cannot get away from it. So because of this global property, Bayesian method is good, but then it doesn't scale, and it's bad for the same reason. Okay? I hope that this gives you some idea of what's going on in here. I want to give another example of this, lifelong learning type of setting. And here again, imagine that you have this classification problem. So you have two classes, and your goal is to draw a line in between to classify the two. Okay, and here you have red line and blue line, right? And you want to now pick one of these two. Okay, so if I ask you a question, and if you're familiar with some of machine learning, then most of you would go with this blue line, which makes sense because this is looks like that it's a little bit more minimum norm solution. It's perpendicular to your data, but this one has a little bit less margin here, so it's less stable. But my point here is that you don't actually know, because you have somehow assumed that what data points you see right now is everything that you're going to see ever. But if you're in a lifelong learning setting, or if you're in a setting where your environment changes, you don't know what kind of things you're going to see in the future, and you have somehow assumed that you're not going to see anything here that will contradict your opinion, right? So what if, like, I saw the next set of example to be this class appears to be here, and then this class got more data here. Now you see that this blue line was misclassified this data, right? I mean, again, when you made this choice at a younger age, when you were younger, you thought that this is how the world's going to look like. But you don't know what's going to happen next, and you're fooling yourself by trusting your data too much, right? So this is a contrived example. It's cheating a little bit, but it's trying to give you an idea of not trusting your data too much because you don't know. And that's what you need to focus on, what the model does not know. And this question is extremely important. You're given some data right now, but you shouldn't trust it too much, because it's not everything. Things might change tomorrow. Things might change in a week. Things might change in a year. Okay. So Bayesian approaches actually can solve this problem, and they don't have this issue because they don't have this problem of picking the one best model. Okay. So as I said before, like in this scenario, if you use this Bayes rule, so here what I've done is I've called this first data set to be D1, and I have a prior distribution, and I basically just did the thing that I told you before. And I got this weight on each line. And it's actually saying that this line is the most important line. It makes sense. But then it's saying that this line is actually not the worst one. I mean, it still has some probability. It looks like it's pretty bad, but it's still there in the pool. So you're carrying this weight around of having all possible explanation of the data with you. Your bag is very heavy, but then you're more safe because you have more tools and accessories with you. Okay, so it's not really the most minimalistic approach, the Bayesian approach. Now what happens is that if you see this data, now you have a choice to be able to update your weights. Okay, so now you're saying, oh, I got this data. Oh, well, this line doesn't look good anymore, but this one looks good. So how do you do this? You just run the same mechanism. You say, I'm going to use this posterior as my prior. I don't have to go back and look at my old data, my old experiences, but I have this posterior in my brain. And my brain tells me that this one had less weight, but now I saw this evidence, I'm going to update the weight of this, and I'm going to give less weight to this one. Okay, so that's what this is doing. It's updating your posterior after you have seen the next set of data points. Now with this, you update the thing, and now you say this one is the most likely one. Okay, so you give most of your weight to this one. So you're safe. Again, you see that the global property, what I call it global property, meaning looking at all possible models that you have in the world. This property makes you very heavy and bulky, and it doesn't scale well. But then it's actually giving you safety because you know you can pick and choose of what to do today, what to wear today. But you'll have to look at your closet, you know. Your closet is really, really big. You need to look at it, but you can pick the best dress that you can wear today. But if you're a deep learning person and you already made a choice of outfit before, you cannot change it today. Okay, I don't know why I brought it on to fashion, but that's one example that came to my mind, and it's fun. Okay, so with that, we are at the end of this part. So what we have learned is that Bayesian learning and deep learning, there are two different types of learning frameworks. The algorithms are very, very different. This one is very local. So you're looking at only one theta, and you're updating it using these mini batches. And the mini batches are very, very local thing. They tell you about your current thing that came in, and then you somehow use it to update your one model. Right? So it's very local. It's based on differentiation. So differentiation is really local thing. On the other hand, Bayesian learning is the other extreme, that it's looking at all possible explanation of the data. And that's why it's relying on this integration, this global property. Okay? And because of that, you have the safety net that you can estimate uncertainty. You can perform sequential learning because you don't forget anything, you know. Everything is incorporated into your posterior distribution because it contains all possible ways of explaining all of your past. And then you can update it. But then this is very, very bulky. It doesn't scale well. And it seems hopeless because you're looking into a lot of things. So it doesn't really work very well for complex models. Okay? So I hope that this becomes clear to you, is why these methods are different and why they have some pros and cons in terms of where they work well and where they don't. Okay, so with that, this is kind of finished the background part of it. And now what we're going to do is we're going to jump into this deep learning with Bayesian principle, how to put these two ideas together. And the first main part for this new thing would be to explain Bayesian principles and how computing approximation helps you to put these two things together. Okay, so I still have 8 more minutes to go. Do we go for questions now? We could do that, or I could explain some more things before we go for questions. How should we do it? Rodrigo? Hi. I cannot hear you for some reason.
Can you hear me now?
Yes, I can hear you.
Perfect. So the first question is, how do we can quantify the prior in such cases?
How can we quantify the prior in such cases? That's one of the hardest questions to answer. So my answer is I don't know. And this is something that is kind of the thing that people start with. So I can only give you an intuition of how this works. And the thing is that what you want to do when you want to do this kind of prior, let me actually go back to here, right? So when you sample from your prior, what you want is you want to not give low mass to an important area. So your prior should be incorporating, not discarding anything in the future that you would see as evidence, So if your prior is too strong, if suppose the width of these lines was very, very thin, then anything that you will see in the future, it'll take a lot more evidence for you to correct against it. So your prior should be flexible to not discard the new knowledge, but to help you to actually focus on important places. But then this is like you don't know beforehand. So usually people want an uninformative prior. Sometimes people have domain knowledge that they try to put in the prior. For deep learning, I would say you don't actually know. For deep learning, uninformative prior should be good, but we don't really know how to put those. So usually we just use like very, very weak prior right now because there's a lot of data that people are using, but that's not the best approach. But I would say this is open for, it's an open problem for research.
So another question is, if doing Bayesian inference, should we care about balanced classes in the training data?
So ideally, the Bayesian approach should be able to accommodate for any kind of issues that you have in the data, as long as your model class is, is not like negatively affected or too much dependent on the data. Okay, so this kind of issue of class imbalance, it should typically be better handled with Bayesian methods. So I would not say that these problems are solved, right? Because it always depends on the class of models that you use and how you validate your results. And you can always fool yourself and do the wrong thing. But the Bayesian methodology has enough flexibility for you to be able to automatically handle issues in your data. But you still have to be careful. But it's better than what you could get from a frequentist approach. That's what, as a Bayesian, I will say. And maybe frequentist people would say that that might not be true, but it's mostly true.
And we can cover a third question. So how do you check if the Bayesian approach is applicable to real data? How do you go when you have a real problem?
That's a very good question. Actually, all these questions are very, very good question. And there's no clean answer for anything. And I'm sorry, I'm not able to give you a very clean answer. But so I could give you instances of how you would do this. So if you have data and it's extremely large, and it's your data, the evidence, you trust it quite a bit. So you think that they all come from some kind of IID setting where the more data you get, it only confirms your belief. then you're in an easy setting and you're going to have enough data and you're going to work with normality. We call it normality, meaning that as n tends to infinity, your the neighborhood around the model fit, the local minimum, becomes more and more quadratic, and things are actually fine in that case. But when you deviate from this kind of a process, so you're in a finite data limit, or your data is actually very highly correlated, so you see things right now. So I mean, coronavirus is an amazing example where your data is actually highly correlated, like depending on where you're testing it, and your data is localized. So if you have outbreak, it only happens in New York. Then everything is kind of, if you look at New York only, then you're super biased. If you look at like the whole country, then it'll look like that the outbreak is not happening. But now it's happening everywhere. But a few months ago, it used to be like that. And when your data is coming highly correlated, then you know that if you did this kind of approach where you assumed everything to be IID, it will not work. Right? So there, a Bayesian approach is more suited, and for actually for COVID-19, lots of people have used Bayesian approaches for that. So this is one example. And what I'm actually trying to say, in general, a rule of thumb that I could say that if you believe that you should not trust your data or your model too much, is that there is life beyond what you have seen right now in hand, and that may not represent the truth that you're trying to seek, then you should use Bayesian principles or Bayesian methodology. And I think this is true in most difficult cases, especially with this kind of black swan kind of thing. Okay, that's my answer.
Great. Perfect. So maybe we can continue with the next part, and then we can address more questions a bit later.
Yes, so we take 10 minutes break right now, right?
Yes, exactly. So now for the break, you can just mute and turn off the video, and then we can reconvene in 10 minutes.
Okay.
If you prefer. If you want, we can continue.
Can I actually like log out, restart my computer, and come back?
You can.
Okay, I will do that.
All right.
Just to avoid any issues. Okay, thank you. I'll see you in 10 minutes.
All right.
Bye.
Bye.
you hear me?
Yes, we can hear you.
Great. Start here. You can see the screen now.
Yes, we can.
Okay, let me. Right. Yeah, I think it seems everything's fine. I can start again.
All right, then let's continue.
Okay. So okay. So what we're going to do in the second part is that we are going to introduce the Bayesian principles that will help us to put the deep learning and Bayesian learning together. And we're going to introduce this idea of approximations and how you can estimate approximation using an algorithm that then will help us to derive many existing algorithms. Okay. So before I get into that, let me just put a big picture a little bit when I say Bayesian principles. As you can see, as you know now, that it's all about sort of computing integrals with respect to probability distributions. And there's different things that you could do. So the thing that I talked about before is computing the posterior distribution, right? So something like this. What I'm going to do is I'm going to approximate it, and I will denote the approximation using Q. Okay, so the P is like the modeled exact thing, but Q is an approximation, and it's theta given D, meaning it's parameter given the data. Okay. There are other things that people focus on. So there's other kind of integral. So this integral is like computing this normalizing constant. But then there is an integral that you might want to do some, for example, when you compute the predictions, you have your posterior and then you sample from it and you approximate it together. And this is used in Bayesian deep learning quite a lot. So lots of people argue that doing this averaging, this computing this integral, it actually helps. So MC dropout and swag and other things, they're all focused on this part. Then there's other things where you are given this posterior distribution, then you're not interested in all parameters. So maybe you're only interested in the last layer of the neural network or somewhere in between. And so you marginalize out all the other layers. Okay. So this type of thing is called posterior marginalization. This is also an integral. So there's a variety of ways that the Bayesian method can be used. They're all about integrations. And what we are doing here, when we say Bayesian principle, we're actually focusing on posterior approximation. Okay, and we are doing this approximation in a particular way by using an optimization reformulation. Okay, this will become clear later on. But remember that there are many other things, but we are going to focus just on the approximating the posterior. Okay. The main idea to put variety of learning algorithms together is to introduce the approximation of the posterior, as I did in the previous slide, and use a particular algorithm that I am calling Bayesian learning rule. Okay? This learning rule will try to approximate the posterior. Okay, and the posterior approximation can be from very simple distribution to a very complex one. Okay, so what will happen is that as you go in this spectrum from very simple to very complex, then you start to get different variety, types of algorithms out of it. Okay, so that's the basic idea. So just think of your true posterior distribution, for example. Suppose it looks like this. So it's on the complex side because it's really looking into all possible explanation of the world. So it's putting, mass over many types of many places in your parameter space. Okay. In this case, just for illustration purpose, it's two-dimensional, but it's still a complicated distribution. what you could do is you can say, I don't care about where it's putting the mass. I only want to somehow estimate the mean of a Gaussian distribution. Okay, so it's like a circle. The circle could be like very narrow or very wide. You don't care about this. You fix it. You don't want to learn it. But you only want to learn the mean. So it's like you're trying to center the circle somewhere over this complicated curve shape. Okay, so if you do this and you use Bayesian learning rule to estimate the mean, what I'll show you is that this becomes gradient descent, meaning that this algorithm reduces to a gradient descent algorithm. Okay, now you can, instead of using just a Gaussian with the mean, you could change the shape of the circle. So you can have covariance, and you can learn the covariance as well. So here, a fit would look like this, that you're trying to get the spread in one direction. So you're saying now that these parameters are also important. Maybe the most important somewhere in the middle, but these are also important. So you've expanded a little bit, and it's a little bit more complex approximation. And if you do this and you use Bayesian learning rule to estimate the mean and the covariance, then this will turn into something like Newton's method. It makes sense because you have mean and the covariance, and covariance is like trying to think about the shape around the neighborhood. So it cares about the Hessian. Okay? Now you can continue like this, and you can use like a mixture of Gaussian. So I put a Gaussian like this, I put a Gaussian like this, I put a Gaussian like this, and it's trying to capture the shape, the spread. And if you do that and you look at the algorithm, it becomes an ensemble of Newton's method. Okay, so you have these different shapes, these different ellipses that you need to estimate, and you run multiple Newton methods, and each of them give you a Gaussian, but then they all interact with each other to kind of spread out to cover different places. Okay, so one covers here, other covers in that direction. They're going into different directions. So I hope that this cartoon slide gives you an idea of what we're going to see, is that this algorithm will convert into many types of other algorithms as you change the type of approximation. And the principle is that you should try to approximate the posterior distribution. That's the Bayesian principle. And if you continue like this, go to the most complicated form that you could choose, then the Bayesian learning rule would just turn into Bayes rule. So it's kind of complete in that sense that it reduces to lots of things from simple to complex. Now, this is all supposed to be written in this paper that I have been writing for some time now, and it's still not complete because there's so many things that we need to write. But you can check out a copy of this. It is version 0.7, I call it, because it's sort of 70% complete. Okay, but hopefully this summer I'm not doing anything other than doing this, so this should be complete soon. But most of the things that we talk here are there in this paper, and it's available on my webpage. Okay, and I apologize for typos and mistakes because it's still kind of work in progress. Okay, so let's start with the form of approximation, and then introduce the learning algorithm, Bayesian learning rule. And then after that, we'll start to derive deep learning algorithms, okay? So the first piece of the puzzle is what kind of approximations you use. And we're going to use an exponential family approximation. And if you don't know what that is, you just don't have to worry about it, okay? But for completeness, I have added it here. It's the exponential family takes, it has exponential here, and it's linear in some sort of sufficient statistics, okay? And the thing that appears in front of the sufficient statistics is the parameter, okay? So this parameter, for example, if it's Gaussian distribution is an exponential family, so you can write the Gaussian with a quadratic. So this is the mean, and this is inverse of the covariance. We call that precision matrix. You can actually write it in this form. So you can sort of take the linear term here. So this is the linear term. And this S times M is the first natural parameter. and then you could take the quadratic term, and s divided by 2 is the second natural parameter. Okay, so this is this, and this is lambda. And theta and theta theta transpose are sufficient statistics. Okay, so there's two sufficient statistics for Gaussian, and there's two natural parameters. You don't need to know anything other than that if you don't want to. So just think of Gaussian always. Think of it having natural parameter and sufficient statistic. The other thing that we need to know is the expectation of the sufficient statistics, and it's called expectation parameter. So you can see that the mean and the covariance precision is the base parameter. From that you can derive the precision, the natural parameter. But when you take the expectation of these two things, like expectation of theta, you get mean. Expectation of theta theta transpose, you get correlation matrix. They're a function of mean and the precision, right? So they're a function of the natural parameter as well. So just need to remember that there's two parameterization: natural parameterization, expectation parameterization, and of course mean and the precision. That's another parameterization. But we're going to work with just these two. And if you don't follow any of these details, don't worry at all about it. Just remember that there is Q, which is the approximation. It has some natural parameter. It has some expectation parameter. And that's all you need to remember. Just remember lambda, mu, and Q. Because I hope that helps. You don't have to worry about all this math. You can read the paper and learn about it later on. Now that we have specified the form of approximation, then now we can jump into Bayesian learning rule. And after this slide, we are ready to derive algorithms. So what we're going to do is, instead of doing this kind of approach where we minimize the loss, which is what we do in deep learning, we're going to minimize a slightly different objective. Okay, and this objective is going to look into this distribution Q. Its goal is to find the best distribution in a class of distribution. So think of like this being class of Gaussian distribution. So all natural parameter that belongs to Q are all mean and precision or covariance. You want to find that mean and covariance. Okay, and you're going to do that by taking your loss that you had in deep learning, and you're going to take an expectation of that. So it's sort of the thing that you saw in that picture, that you draw a line and you draw many lines and you look at the loss over all of these models. Okay, so that gives you an expected loss, and this will depend on the mean and the precision of the distribution. It doesn't depend on theta because you have integrated out theta. So it doesn't depend on that particular one line, but it depends on like how those lines are spread out, where those lines are centered. Okay, so it depends on the mean and the covariance. Then you don't want all of these lines to collapse on each other, so you want them to be slightly random, spread out. So you're going to penalize the entropy. So it's going to be the regularization. Okay, so again, don't worry about it if you don't follow all the details here. It's less important. Remember that this objective is over the loss of 1 point theta, and this one is over a distribution. And you're trying to find a distribution here. So this is more Bayesian. And we'll show later how we'll get into the math of this after we have seen the relevance. So we'll just first see why this is important, but later on we will get into how to derive this. Okay. So just imagine these two problems. This is non-Bayesian, more deep learning. This is, you have to trust me that this is a Bayesian approach. Okay. Then deep learning algorithms look like this, right? They correspond to this objective function. And what we're going to do is we're going to write a very similar algorithm for this problem. And that algorithm will look like this, okay? So what's going on here? So it looks pretty much like this, that you're updating the parameter, but now the parameter is not theta, but you're updating the parameter of the distribution. And you're updating the natural parameter, that's lambda. It's related to the mean and the covariance, but it's slightly written in a different form rather than the mean and the covariance. Okay, so you're updating the natural parameter. You have a step size, learning rate, as you have in deep learning algorithm. you have loss, but now instead of taking the gradient of the loss, you're taking the gradient of this whole objective because that's where you're optimizing. And the last detail is that instead of taking the gradient with respect to lambda, you're taking the gradient with respect to expectation parameter. Okay, so this is weird at first, but this is what it is. Okay, later on in the part after this, we will try to derive these things and understand how you come with this objective and this algorithm. But for now, just think of this as Bayesian learning rule, an alternative to a deep learning algorithm. It's gradient based, but the gradients are computed with respect to mu instead of lambda. But you update lambda. Okay. So hope that this is clear. And what's going to happen now is that we're going to show that when you choose an appropriate approximation from simple to very complex, like having a circle to having an ellipse and to having multiple ellipses, and then doing some tricks on not being Bayesian. So not really looking into the many models, but looking at one model, we can recover deep learning algorithm from Bayesian learning rule. Okay, so we're going to show that this is a superset of this, that this explains many algorithms that exist in practice. Okay, so that's finishes this first main part. And now we are going to go to the second part. We're going to derive deep learning algorithms from this. Okay, and I won't stop for question right now. I'll try to finish this part and then try to get into questions. Okay, maybe I'll finish the deep learning part and get into question after that. Okay, so let's start with the simplest algorithm, gradient descent and stochastic gradient descent, and see how Bayesian learning rule reduces to gradient descent. Okay, and this is actually the simplest example that is there. The details are in this paper. You can find the detailed derivation there. Okay, so gradient descent takes this form, and what I claim is that if you choose a Gaussian distribution with a fixed covariance, what I'm going to do is I'm going to fix the covariance to be 1. It doesn't have to be 1, but I'm just going to choose it to be identity matrix. Okay, and I'm going to try to estimate the mean. And if I do this, then I will get gradient descent from Bayesian learning rule. Okay, and I've written the other details of what the natural parameter is, what the expectation parameter is. You can do this math on your own. The entropy is a constant. It doesn't depend on the mean. So it's a very simple example. What we're going to do now, we're going to just kind of plug these things in the Bayesian learning rule. Okay, it's very straightforward manual exercise. So you know lambda is m, so you put m here. You know mu is m, so you put mu here. And you know entropy is constant. So if you do that, well, that's what you get. Lambda is m, m, and m. And because entropy is constant with respect to m, it just kind of goes to 0. The derivative is 0. Okay, so get this. So now you see that this already looks like that. Wow. Okay, so that's very simple. The only difference here is that it's the derivative is going through this distribution. So Q has a parameter m, not L, right? But here the gradient is of L, of the loss. Now to get from here to there, you need to kind of give away the Bayesian properties. So you see what's happening? That this is saying that you need to sample theta from Q, plug it in there, add it all up, and then take the gradient of that with respect to the, where the samples generated. So that's the mean of the Gaussian. But you can sort of like ignore that global property. Instead of sampling and looking away from the mean, let's just look at the mean. And that's kind of being greedy, being like frequentist about it. So you push the expectation inside the loss. Expectation of theta is m. I call this global to local approximation. In statistics, there's a name for this. It's known as delta approximation, where you ignore the higher order statistics about Q and only focus on the mean. So it's just kind of you do Taylor series approximation and then you just kind of ignore all the other terms. That's basically what it is. And this is like 100 years old method. Okay. If you do that, then you see that you can, this becomes just that. So you have gradient of m. Now if you call m to be theta, you get as gradient descent, right? So it almost looks like cheating here, that I've cheated here, but you will see that the same principle, the same working just repeats itself now, okay? So you know almost everything that you need to know. And now it's just kind of just doing the math, you know, just kind of manipulations. If you want stochastic gradient descent, just replace this by stochastic gradient, and it'll be stochastic gradient descent, okay? So that's the procedure, and we're going to repeat this again and again, and we'll try to then think about the insight of what insight we get when we did this, right? So here, what we basically did is that we did nothing. We chose the Gaussian approximation, and we don't look into the covariance. So we're ignoring sort of the second sufficient statistics of the Gaussian. We're only looking into the first sufficient statistics, which is the location of the Gaussian. Okay, and we ignore the Bayesian property, right? So these two things sort of led us here. So then a very natural question that arises, that because I've ignored the second sufficient statistics, the spread of the Gaussian, is it possible to estimate the covariance from SGD? Okay, and this is sort of an open question that people have worked on, and lots of people have worked on. What people have shown is that if you take stochastic gradient descent, and if you set the step size to be a constant, then what happens is that it goes around, and in the end it doesn't converge. Okay, so it does randomly walking around the solution, it doesn't converge. And if you look at these iterates that are spread around the minimum, then that spread gives you some kind of Bayesian approximation. Okay, so you can form a distribution from the iterate, and it was, I think this has a long time ago, people have actually talked about this from what I remember. But this paper formalizes this using an AR process as a continuous process that SGD is running around. You try to approximate the covariance or the spread of the Gaussian from it. There's another paper that shows that stochastic gradient descent is actually doing some kind of approximate Bayesian inference using diffusion equation from a homotopy. That's a different approach, but it leads to the same result. And then Andrew Wilson's group, people have come up with a very simple method to estimate uncertainty in Bayesian deep learning from this. So the question is, from our derivation, can we say something about, like, can we obtain covariances from SGD iteration? Okay, so can we do a poll right now on this?
We have it live, so everyone please see the link in the chat, just click on it and you can vote.
Somehow I'm not able to see. Am I able to see? Yeah, I can't able to see.
Yes, it is in Slido, so everyone should just click on the link that is in the chat box, and then they can answer.
I'm very scared of clicking anything because I might give the answer away.
No problem. I can tell you actually how it looks like.
Okay.
So, moment, yes is winning by so basically 9-1.
Great. So that's again, the question, there's no clear answer for questions. They're always like meant to make you think. So the answer is sort of yes and no. And the answer is yes and no because what SGD is actually doing, SGD is estimating only the mean. That's what we are seeing from this derivation that we just did in the previous slide. And the covariance choice is actually can be arbitrary, meaning that if in the previous derivation, if I choose Q of theta to be some other, fixed covariance, so I'm not learning it, but I let this be like some sigma, then the Bayesian learning rule will give me this update. Okay, what essentially this is saying is that I can arbitrarily make my steps much larger. I can have this preconditioner that will make it much larger or much smaller, and I will converge to the same, similar solution around the neighborhood, but it'll kind of make my spread larger or smaller. Okay, so you see that the choice of covariance is actually, it can be arbitrary. And I will really, with this insight, I will encourage you to read these papers. And what you will see there, that essentially the analysis always comes down to this preconditioner. Meaning, how do I choose the step size? How do I choose the noise in the gradient that lets me flicker around the local minima? And this is a free parameter. This is a free thing that you cannot decide just from the SGD iteration. So the answer is yes and no. In principle, yes, the iterations give you something that resembles an approximate distribution, but it depends on the choice of this preconditioner. And this is what you would get. So these are very complicated, mathematical analysis that eventually comes down to this simple, conclusion that the preconditioner has to be tuned. And if you tune it properly, there is a place where you can minimize a KL divergence between the approximation and the true posterior. Okay. And so the point is that the estimation of the covariance requires an additional computation. That you, just by SGD iterates, cannot tell how much the spread should be. The choice of step size, the choice of mini-batch size, the choice of momentum, it actually affects your iterates. And it can be arbitrarily large or arbitrarily small. And for you to fix that, you need to use a preconditioner, which actually informs you about how large these steps can be. Okay, and you can see that this covariance should be something related to the noise in the stochastic gradient. And if you choose this such that it cancels the noise, then you're sort of doing the right thing, because you're making the left and right hand side same. So I'm not going to go into the detail on this, but please read the paper that I told you, the learning algorithm from Bayesian principle paper. There's some description about it, why estimation of covariance requires additional computation. Okay, so we'll get back to this point after doing Newton's method and look back at it. But let's try to now, because we see that just by using SGD, we get the information about the mean. So it's obvious to say that let's try to get the information about the covariance. Okay, so we're going to do that now. So we're going to try to derive something like Newton's method, and that's where the answer is. Okay, so Newton's method takes this form. H is the Hessian here. And what I claim is that if you choose the Gaussian to be a multivariate Gaussian, so Gaussian with mean m, and the covariance, so I've denoted the precision is S, the covariance is inverse of it. Okay, and the natural parameter, expectation parameter are these things, and then the entropy is like log determinant of the covariance, but you don't have to worry about that. But my claim is if I choose this distribution, I'll get the Newton method. Okay, so I'll do the same trick. This is a little bit more complicated. There are a few more steps in there, but if you read the paper, it's all these kind of put at one place in that paper. So I do write the Bayesian learning rule. I plug in the definition of lambda and mu. But before I do that, I'm going to make one more simplification. I'm going to use an identity that the gradient of the entropy with respect to the expectation parameter is equal to the natural parameter. Okay, this is a beautiful property of exponential family. This is related to Bregman divergence, and the detail of this is there in the learning algorithms paper that I have told you before. Okay, but for now, just take my word for it that this gradient is just lambda. So the gradient of this term is just lambda. So I could just kind of rewrite this is this, and this I can infuse with this. So I just kind of rewritten the rule, okay? Just some mathematical jugglery, don't have to worry about it. And now I'm gonna plug in the definition of S and mu, okay? If I do that, I put the first natural parameter, I put it here, and then I have the gradient with respect to the first expectation parameter, okay? See? Then I plug in the second one here, and I put the gradient with respect to the second. So it's very like, mechanical. I just can plug in the mean and the correlation. So you can see that now these should go somehow to the gradient and the Hessian of the loss, right? Do one more simplification. I just removed the half from here. I hope you could see that. Just remove the half, and I get that. Okay, so now I have 2. And now, so I'll go to the next page. So this is what we derived in the previous thing. And this doesn't at all look like this right now. It's just so far from it that you will think like, why would this turn into that, right? And that makes sense. But there's a magic trick. So essentially, what you can do is you can write the gradient with respect to the mean and the correlation in terms of your gradient in the Hessian. Okay, and it's a magic identity. And it's there in the paper. You can read the paper. So it's also in this paper, and it's also in the learning algorithm paper. But essentially what this tells you is that the gradient with respect to the first expectation, so the mean, and the gradient with respect to the correlation are written in terms of the gradient of the original loss, the Hessian of the original loss, and the Hessian of the original loss. You see that this gradient is with respect to theta, and theta then sampled from Q and then averaged together. Okay, so it's very much like what we had in the gradient descent derivation, that you get that. Okay, so again, this requires half a page of derivations. Not that actually complicated, but you'll have to take my word for that. The main idea is to see that when you take these gradients with respect to the expectation parameters, they tell you something about the gradient of the original loss. And this is remarkable. This is very surprising, because you're actually taking the gradient through a distribution. It's the parameter of Q. But it ends up telling you about the gradient of the loss, of how loss is shaped, right? Is this landscape of the deep learning loss. So Q is actually helping you understand that, and we'll see a very nice visualization soon, which will shed some lights on this. But this identity actually tells you a lot about what's happening when you're taking derivative with respect to parameters of a distribution. It helps you to probe into the original loss. So I'm getting carried away now. Let me get back. What we're going to do now, that because we want to get the gradient, not the expectation of the gradient, we're going to do the same trick that we did. So we're not going to be Bayesian. We're only going to look at one point. And we give away the nice Bayesian property. So I push the expectation inside. And if I do this to both of these things, then I can write this update in this form. So essentially what I've done here, this guy's just this, right? So this becomes that, and that becomes this, because I push the expectation inside. So I hope that convinces you. The same thing I do here, that I multiply, well, there is a little bit of more manipulation here, because you have to plug this thing in here, you have to put some things together and then simplify. Don't worry about it. But now once you use this, you see that this update now is looking more like this. You see that mean is like theta, and gradient with respect to mean is gradient with respect to theta. So you got that right. And now your preconditioner is not Hessian, but it's kind of a moving average, some kind of running window of the Hessian. Okay. So what we could do, you set the step size to 1. Because you may assume when you're doing this kind of Newton's method that you're close to this convex setting where you can do good Newton step, which corresponds to having a complete quadratic approximation. Then you essentially get the Newton thing. Okay. So hopefully this convinces you that the Newton's method can be derived from the Bayesian learning rule. So I just want to summarize this and sorry. So this hopefully is fine, and I want to summarize and shed some light on why this is insightful. What we have done is that to estimate the mean and the precision, we wrote this type of update, and when you set rho to 1, you get the Newton method, right? But what this update is actually telling you is that you can compute Gaussian approximation from second order optimization. So if you had the gradient and the Hessian, it'll help you estimate the Gaussian distribution, right? What it's telling you is that estimate of the mean requires first order information, but the estimate of the covariance requires the second order information. Okay, and this is actually written, I mean, this is sort of known but not appreciated as much, or not written in this form. So there's this paper. This is a beautiful paper to read if you want to learn about approximate Bayesian inference. It only talks about the Gaussian case for Gaussian process models, so it's a little bit narrow. But essentially, this kind of thing is known that if you want to estimate a Gaussian approximation, for example, using Laplace approximation and variational inference, then you essentially get this result that the first order information gives you clues about the mean, and the second order information gives you clues about the covariance. Okay, so the point here, now going back to this SGD thing, can you estimate covariances from SGD iterates? What I'm trying to tell you is that you can't escape this principle. This is a fundamental bottleneck, right? So you can, you have to, if you want to compute the covariances, you have to go to some kind of second order approximation. There is, so you can reduce the computation, you could do heuristics, you can do approximations. You could say, I'm going to run only SGD, let it converge to the solution, then look at the spread, somehow adjust that spread to find the preconditioner. But essentially, in the end, you are looking into some kind of second order estimation. Okay, so what I'm trying to say is that the answer to that SGD thing was mostly no. In principle, no, but in practice, you could do something to get the second order information. But you have to do some computation to get it. Okay, I hope that this actually helps you to understand many efforts in Bayesian deep learning that only try to run simple first order methods and then try to estimate the second order effects from there. And this is, there is a computation cost that's involved with uncertainty that's not going to go away in principle. Okay. Now, another insight that I want to give you is this difference between the optimization solution versus the Bayesian solution. Okay. So you see that I push this expectation inside. But what if I didn't? What if I didn't make that really lame approximation that I think, where I pushed, I ignored the samples from the model, from the distribution, rather only focus on the mean. Suppose I didn't do that. Then I would get this update, right? This is what Bayesian learning rule gives me. And if I look at the fixed point of this, so where does this converge? Well, when mean is equal to mean, then this gradient, this term should go to 0. Okay? When S is equal to S, then S should become expectation of the Hessian. Okay? So this is sort of fixed point of the Bayesian learning rule. Now, this fixed point helps you to look at the optimality condition and compare it to what you would get if you did plain optimization. Okay? So if you did optimization, what you get is gradient needs to be equal to 0. Sorry about this. And the Hessian needs to be positive definite. But in contrast, if you look at the Bayesian solution, it tells you that the expectation of the gradient has to be 0. So you're not just looking at one point, you're looking at the expectation, you're looking at many, many solutions, okay? And you're not looking at just the Hessian, you're looking at the expected Hessian, and you want that to be positive definite. Now, this is looks very theoretical, looks of like no consequence. Like this approximation that I do when I push this expectation inside to go from here to here, it seems like a hack, but it's not. This is the property of Bayesian principle, is to have that expectation. And if you lose that, then you're not Bayesian anymore, okay? So you actually miss out on Bayesian benefits. What are those Bayesian benefits? And I just want to give you this example and make you think a little bit of what do you lose when you go from the optimization to Bayesian land, okay? Sorry, what do you gain when you go from optimization to Bayesian land, okay? So think of this problem. This is a loss function. And in this is the minimum. So this is a W star. And the W star satisfy this condition, right? So the gradient is 0 here, and the curvature is positive definite, so it's a minimum. And if you move along this side, suddenly your loss grows. So you get really high loss. And this is a very, very common scenario in logistic regression in classification setting, because you are, your 0-1 loss makes you this kind of wall next to your optimizer. So you're very close to things. And if your data changes slightly, you might actually be perturbed and you might go into this side, which is very dangerous, okay? So now I want you to think, instead of this stationarity condition, optimality condition here, the Bayesian solution will have this stationarity condition. So where should the Gaussian solution be? Where should the mean be? So Rodrigo, if you could put this question on poll, please check the polling place. There's a question there that should ask you the question. The question is, where the mean of this Gaussian going to be? Is it going to be on top of this W star? Is it going to be on the left-hand side? Or is it going to be on the right-hand side? And why? And I want you to think about it. So I'll take 1 minute and I'll wait for your answer. Is the question online?
We're putting it live now, so 1 minute.
Okay.
Yes, now it's live. So please, everyone, go to Slido and answer it.
Do we have the answer?
Yes, so from the 3 options, the large majority, so they voted for at the right of W star.
Okay, good. Great. So yeah, I think I already was giving you the hint. But what I wanted to see is that if you can think about this through these optimality conditions, right? Because that was my goal. Hopefully you got a sense of that. And if you didn't, then the answer sort of looks like this, right? So actually the slides that I posted on my website don't include these plots on purpose, but I will update it after the talk. I didn't want to give you the answer beforehand. So what is happening here is that you want expectation of the gradient to be 0. Now, if you look at so if you go like delta on this side and delta on this side, you see that on this side, the gradient is extremely large because of the large slope here. While on this side, the gradient is small, right? And you want these two to cancel. The gradient on that side of the mean to be canceled to the gradient on this side, because that's what you want. You want this to go to 0. So you're going to place mean at such place such that the gradient on the left side and gradient on the right side are of opposite signs. And if you want to do that, you know that you have large gradient on this side, so you will shift your mean to the right. Okay? So if you think a little bit more about this, it'll kind of become clear. But this is a really, really beautiful, one-to-one correspondence between the optimization and the Bayesian solution, that the Bayesian solution seeks robustness. It's not greedy. It doesn't look only at the gradient of the Hessian at this point. Rather, it looks at the gradient of the Hessian at all points. And it's trying to average them and look for a place where things cancel out. So it's a more stable place. Things don't move there in the neighborhood that much. So it will give you slightly worse loss, but it will avoid a large, if a large loss on the right if there is some changes in the data. If you perturb the solution, this will take a lot more effort to get to this large loss than this one. Basically, it's saying if you're standing next to a cliff, don't stand right next to a cliff. Stand a little bit far from it, because anybody can push you and knock you over. Okay? So that's what this happens. I mean, this in the paper, Learning Algorithm from Bayesian Principle paper, there's a whole page of discussion on why this is important and how this condition is actually general. So you can take the whole Bayesian learning rule, you can always write this optimality condition, and this kind of helps you to go beyond the second order optimization as well. So this is very, very powerful, and this is much more general than that. So second order optimization is actually a specific instance of this where you push this expectation inside, okay, and not be Bayesian. Now here is another example of robustness. In this case, you have a sharp minima and you have a flat minima. And again, you can go back to the optimality condition and you can argue that here the expectation is less stable because the neighborhood changes very, very quickly. And if you're given the choice between this and this, then you will pick this one because this is more stable. Okay, so again, the Bayesian solution helps you to do flatter minima. If you initialize on this side, optimization algorithm will almost with probability 1, given the step size, it will converge here. But Bayesian solution, if you initialize them here, and if you let the covariance be large, it will actually tunnel through this solution, and we'll get to this solution. There is an example in this paper. This is on arXiv, actually. There's also another example that Farhan Kassar has written, and we sort of did the same example and try to show how a Bayesian approach where you have expectations, it will tunnel through these local minima and go to more flatter solutions. Okay, so hopefully that convinces you of why Bayesian solution would be better, and we'll get back to it when we'll try to improve deep learning algorithms. But before that, I just want to close this session by showing you how what we derived in the previous section by using this multivariate Gaussian already helps you to derive RMS prop. If you don't know what RMS prop is, don't worry about it. It's just like gradient descent. So you update theta and you use the mini batch gradient, but you scale it with some kind of vector. And this vector is actually learned through this kind of moving average exponential smoothing where you have 1 minus rho times rho, and you compute the square of the gradient. Now, if you look at this update and if you look at this update, you see that they already have drastic similarity, okay? And I would encourage you to go inside this paper and read. I've written about, last So 1981 and 1986 is probably the first paper on this, where they're trying to use this kind of update in deep learning by LaCoon and colleagues. They're always doing this exponential smoothing to make this scale vector stabilize. And the Bayesian principle actually dictates that you should be doing this. Right? It's saying that you should use a second order method, but this is a cheaper version of that, where you don't have the full matrix. Rather, you only have diagonal of that matrix. So what you can do is you can do certain modification. You can choose a Gaussian with diagonal covariance, and then this will become just a vector. Then you can replace the Hessian by the square of this gradient. So this is a trick that you're doing, not to having to compute the Hessian because it's very complicated. Actually, the older version that are done in deep learning were all using Hessian. And this is like now modern versions don't use Hessians because they don't care about uncertainty. They don't care about the variance information. And because they use the squared thing, they need to do the square root because the scaling sort of messes up. Okay, but if you make these three a further approximation to the Bayesian learning rule, you'll get that. So you can see that modern deep learning algorithms that seem to work in practice have these hacks that are found by years of empirical effort that are directly dictated by the Bayesian principle. Okay, so it's 50 minutes now. Rodrigo, can I take 10 more minutes and then do a break, or do you think it's good to go for a break now?
As you prefer. So if you want to finish, we can push the break a bit later, and then we can do it later. So
I could do 3 more minutes, and then we could do 10 minutes break. I think that'll be... Okay. Or maybe no. Actually, let me finish this part. So yes. I will do the full... I'll do until 9 more minutes, and then we'll take a break for 10 minutes. Okay?
So, okay.
Okay. Thanks. So it's almost finishing. So basically, what I was trying to say is that people have come up with these heuristics with a lot of empirical effort, but the Bayesian principle seems to point us in the right direction, right? And saying that if you want the right covariances, you should be actually using Hessians. But if you don't care about the covariances or the spread around the local minima, don't do it. Or remove the expectation as well. Don't worry about that, right? Because that's not your focus. Okay. If you want to get to Adam, you have to add a momentum term. And there's this beautiful thing that the momentum that Adam uses, it's actually different from momentum that SGD uses because it has weird scaling. But if you use a Bayesian principle and you use a heavy ball term with sort of like a entropy type of heavy ball term, you get the Adam update with very few approximation in hand. And these details are all in this paper. Okay, so I haven't got really into details, but I have given you a gist of how it actually works and to kind of see the differences between deep learning algorithms and the Bayesian principles. And this is all summarized in this slide. So hopefully this helps you to kind of read the paper and then understand the details. Okay, so I will go one step by step here. So we start with gradient descent, right? And that's basically Gaussian with fixed covariance. So don't estimate the covariance, just estimate the mean. And your gradient with respect to mu, the expectation parameter, translate to just computing first order information. Then if you expand and go to full covariance, then your second derivative with respect to the expectation parameter helps you to compute the Hessian. Okay, so then you get the Newton's method from it if you let the step size be 1. But if you don't do that, you get an algorithm that looks very much like deep learning algorithms. But there, if you do, so you use diagonal covariance, then you get these modern deep learning versions where you have a vector scaling. So it's a scaling vector instead of scaling matrix. And there you have to, you don't want to compute the Hessian, then you do certain approximation, right? And if you want to derive atom, you use the moment, okay? So there's many more things, by the way. This principle just kind of works. And if you want to get dropout, then you use a spike and slab mixture. This requires a bit more derivation. It requires you to go to mixture of Gaussian, and that is covered in this paper. The dropout detail will be written in this paper, and I'll probably write it in the next 2-3 weeks, so it should be up in some time. But essentially, if you go to mixture distribution, then you get dropout or ensemble of Newton method. And these methods, the stationarity condition, the optimality condition is different from the second order optimization. So it's already kind of taking you away from second order optimization, doing a different kind of new thing in the landscape. There's more, like if you go to binary neural network where weights are not Gaussian but binary +1 -1, there you can use Bernoulli approximation, the posterior, and that eventually gives you a method called straight-through estimator, which is used in for binary neural network. And this paper, which is published in ICML, sorry, this should be 2020. That paper contains the detail of that. So this principle sort of works for many of those things, okay? So essentially for all of these things that we did, we ignored the expectation, right? We just pushed the expectation inside, because if you're going to go from the Bayesian fixed point to an optimization fixed point, then you need to ignore the Bayesian averaging. So the idea then in the next part would be that if you want to improve the deep learning algorithm, then we just need to add some global touch. Okay, so we're going to just add the expectation back. Just modify RMS prop or add-in to have this expectation go from this side to that side. And then that will require you to change in the code, like just few lines, and that will give you a new method, okay? So that's, we'll see that in the next part when we do uncertainty estimation. But first we'll go through the theory of Bayesian learning rule, how Bayesian learning rule is derived, why do we optimize the Bayesian objective that we optimize, how that relates to other Bayesian inference algorithms like Kalman filters, HMM, and EM algorithm, and variational inference and Laplace. That's what we'll see in the next 20 minutes. And then we'll get into uncertainty estimation in another 20 minutes. Okay, so that's the next part. So with that, I will stop now. And what time is it right now? Okay,
Now-
so I think this is good. So we can meet in 12 minutes, I guess.
We can do that. So now it's 10:58 in Moscow. So then we will meet again at 11:10.
Okay, that's great. So have a nice break, and maybe when we meet back, we can do questions, right, for a few minutes, and then we can start again. Okay, good. So
All right,
please
let's do
post
so.
questions if you have.
So if I look at this thing, one of the questions that we had there was, so we have, considering that RMS's prop and ADAM are derived using different assumptions from the general Bayesian formula, does it mean that they can be expected to converge to different solutions? If yes, would you think such differences could be significant in practice?
Yes, so they do converge to different solutions. And it's the same kind of thing, right? So I showed, maybe I should share screen. I think maybe that'll be good. Like the thing that I showed, right? So you can see my screen, I guess.
Yes, we can.
Okay. So here, this thing that I showed. So RMS prop and Adam and deep learning algorithms are aiming for this, right? But we don't know if they actually get there, right? So SGD doesn't really converge to, if you use a finite, like a constant step size, then it doesn't converge there. And using large mini batch sizes doesn't really generalize that well. So I think there's this noise that helps you not converge to this point, but rather somewhere around is actually helping you to do something better. So that seems like it should be related to the Bayesian principle more than the optimization, but maybe it's somewhere different from both of them. So we don't know this yet. So the solution found by RMS prop and Adam are generally different from what we find with optimization, although they're designed to find this. So there's lots of work on this for the last 10 years. Sharp min-mush, saddle points, and using large batches. Why doesn't it work? Removing momentum, it hurts a lot. So it's not very clear, and I think most things, but so they're related, but not exactly.
Then there's another question. So you say we cannot change our ideas about data in the deep learning setting, but can we use fine-tuning to the new pieces of data?
You can, but like it doesn't really work, right? So of course, in the setting where you have lots of data about the things that you're going to do, and lots of data from the past, and the things are not that different, and you can actually do these tricks in computer vision. But in general, this problem is far from being solved. And what I'm actually saying that engineering like this, tricks like this, would work, until they work, and then they don't work. So, of course, fine tuning does something, and it's towards that idea. It's again very data centric, and what I'm trying to say is that when people solve the similar kind of problems, they are actually not, it's not data. We are learning things about our past experiences. Like we know that ukulele and guitar produce sound that appeals to us. It's not just like, they're not just data points. We understand something about how the world works, and then we are using them. So that is what is required. I'm not sure if Bayesian principle really leads you to that, but I don't see any other way for me. And I think fine-tuning is really lagging in that. So the hope is to go towards that solution.
Yes. These are the only questions we have at the moment, so we can continue.
Okay. Good. Okay, so remind me. So we have until. So we have around 45 minutes.
Yes.
And we want to do maybe like 10 minutes of question in that. Is that enough?
Well, I guess we can just now cover the content, and tomorrow we'll have our Q&A session, the longer one. So anything that has not been addressed now can be addressed tomorrow. So if you want to cover what is pending, you can just go ahead.
Yeah, because I'm actually debating if you want to do, because you also wanted to do other types of questions. And for that, I mean, should I cover something on lifelong learning or not, because it's like a little bit way too much material. So I could skip that part, or I'm not sure what your plan is here.
I would say we have now the 45 minutes left, and then tomorrow we'll have basically another extra 10 minutes for anything that might be a recap, and then after that we'll have our questions.
Okay.
If you believe lifelong learning can still fit in this basically 55 minutes in total, then we can do it.
Okay. It's very difficult, but I will just kind of do a very quick one. Okay. All right. So what we're going to do first part is that now we're going to go into the more Bayesian learning side and try to look into a little bit more into history. And I will be quick here. I'll spend a little bit more time here, and I'll be quick for the lifelong learning case. Okay. Okay. So what I showed you before didn't look like this kind of Bayes rule. So you see here that you use this Bayes rule to get the posterior distribution, but we were writing Bayesian learning rule, and it didn't seem like that it's anywhere similar. What I want to show you is that if you choose the loss to be log joint probability, so this numerator, so it's prior times the likelihood, then essentially this minimum that we wrote before of this expectation of the loss with respect to distribution Q, solution of this coincides with the posterior distribution, so the Bayes rule, right? So the trick is to not restrict the distribution to a set of probability distributions. You just assume this to be all probability distribution that exist. So everything, not just Gaussian or Bernoulli or anything. It's just all possible distribution. If you minimize this objective with loss being this log joint, then the solution of this is equal to the Bayes rule. Okay, and the proof is actually very, very simple of this. You take this expectation of loss, this is entropy, so you write it like that. Then you can take the two terms together, write this as exponential, so e to the power minus loss, and then think about like when will this be minimized? Well, this will be minimized when this is equal to that, because then this becomes 1 and log of 1 is 0. Okay, so this is how you get Q of theta to be equal to this. So what this is basically telling you is that the optimal Q that you will get by minimizing this unconstrained problem will be equal to the e to the power this, and e to the power of the loss, because the loss is defined to be log joint, is just the joint distribution, which is proportional to the posterior. Okay, so this, I'm not sure if all of you follow the derivation, but you don't really have to. The main point is that the Bayes rule that you get is a special case of minimizing this kind of objective. But the good news is that the objective is actually better news, is that the objective is applicable for any loss. Like this loss doesn't have to be a log probability. So it doesn't have to be a probability. It could be an arbitrary loss that you write. And this may not be just like the Bayesian posterior, but it's something like a generalized Bayesian posterior. We call it Gibbs distribution in the literature. Okay, so this formulation is actually quite general. It's actually more general than standard Bayesian inference that we talk about, where you can have a generic loss. And this idea is actually not just, just wanted to give you a little bit of historical context, that this idea is not just used in modern world, but this is actually very, very old. So the oldest, and maybe there are papers even before that, but the oldest paper is this paper by E.T. James. It's a beautiful paper to read. At least the first 2-3 pages of this is very easy to read. And you will see there that he writes about this from a maximum entropy principle. So this is like the entropy, and you can write this in a way that you're maximizing this, and these are like constraints to your problem. They're like new piece of information that is given to you, and you should be adding these new pieces of information such that the entropy is maximized. And that's what this Bayesian principle is actually based on. So further, people realized that this was actually a Bayesian principle, and people wrote about that. And James E.T. James himself, wrote about how the maximum entropy principle is a special case of the Bayesian principle. Lately, some people have written paper on it, rediscovering and reinterpreting this and generalizing this constant context to any loss function. But this idea is very, very old. There's many ideas in pack-based community that think about optimizing the same kind of cost function. And the incredible thing there is that they show that the best solution that you get, it actually, the regret bound, the bound that you put on the generalization error, correspond to an objective that is of this form. So essentially, if you want to generalize better, you should be minimizing this kind of cost function. And this is called pack base. So what it's actually telling you is that the solutions that if you find that should give you better result, should be the solution that coincide with this objective. Okay. So there's a lot of evidence that this is a good objective to aim for. There's more in online learning where this is related to mirror descent algorithm. Sometimes called follow the regularized leader, and then exponential weight aggregates where you are weighing all the things that you've seen. It's basically a Bayesian idea. Okay. Then there's this free energy principle in neuroscience. This is also based on a Bayesian principle. So historical context for this kind of object, there's lots of it. Right now, what we are doing, actually, we are approximating. So we're not letting this P be all set of distribution. So rather, we fix this P to be an approximate. And in the community of Bayesian inference, this is called variational inference. Right? So this is a particular type of set of methods that focus on approximating this. That we learned in this talk using a specific form of algorithms. This is Bayesian learning rule. And if you use this algorithm to estimate Q, then you see that this not only is a general principle to as an objective function, but also it is a principle that helps you to derive algorithms, right? So what I'm trying to actually really push people to see that this is not just a variational inference or an approximate inference method or doing Bayesian inference, but rather this is the way how you see learning algorithms, how you see when you want to generalize better what kind of algorithms you should be running. You should be running something that aims for a Q that minimizes this objective function. So let's go back and think about well, if that's what we should be doing, then how does everything that I learned in the textbook in machine learning, courses, how does that relate to? So least squares, Kalman filters, hidden Markov model, EM algorithm, all of these things that you learn in the books, right? So what actually happens is that turns out that there are also special cases of the same Bayesian learning rule that we've been using in this. Just that you have to define the loss, as we said before, as this log joint. And actually what happens in these cases is that you can actually go inside and you can write this loss in this form where you can split it into two forms, where one that depends on theta and the other that depends on the data. So these textbook examples that you read about, they all are the simple cases where you have closed form solutions. So in these squares, you can just solve a system and you have a solution. Now there, the property is that the loss is always written in the split. It can be expressed in terms of the sufficient statistics and the some kind of parameter that depends only on the data, just like the natural parameter. Essentially, in linear model, you can write least square loss, so there's quadratic plus a quadratic regularizer. You can rewrite it in this form, so you can have x transpose y, which has this sufficient statistics theta. And you can have this quadratic term with this quadratic sufficient statistics. So you can see that least square loss is quadratic. So the sufficient statistics is quadratic. That means that you should be using Gaussian approximation, right? And if you use the Gaussian approximation, then you get the exact answer, right? So your approximation should be e to the power of theta and theta theta transpose. That'll be exact in this case. You can do the math and you can compute the expectation of this. You'll see that because expectation of the sufficient statistics is just expectation parameter, there should be a transpose here. But essentially, when you compute this gradient with respect to expectation parameter, it's just equal to this lambda d. So it's just this. And if you plug in the Bayesian learning rule, you'll do some manipulation. You will see that your optimal lambda star that you get from Bayesian learning rule should just be equal to lambda d. So I'm not going into the details of this, but look into the Bayesian learning algorithms from Bayesian principle paper. This is kind of detailed as an example, least square example that I've written there. Essentially, you just kind of recover least square if you plug in, natural parameter of the Gaussian and you match it with lambda d, which is like this guy and this guy. You plug it in here, you solve system. These are details. I'm going to skip this. Okay. So essentially, what I'm saying is that all of these textbook things that you learn, they're all equal to this equation. Compute lambda d, write the loss, read out the part that depends on the data, set it to be equal to the optimal natural parameter of the approximation. So like Kalman filters, HMM, they're essentially equal to this equation. Stochastic variational inference is an approximation, variational message passing, where you can't perform this operation directly. So you try to do it coordinate-wise, and it's essentially trying to solve this equation. Okay, so it's related to lots of things that you have read in the textbooks and you read about in the literature of approximate Bayesian inference with many conjugate things. That's what it's called. Another method you might have heard is Laplace approximation, where you take an optimization algorithm, you run it to convergence, and then once you converge, you compute the Hessian. That gives you a Gaussian approximation. So that is essentially just kind of running this Newton type of method that I talked about before. So you run this is like this M converges to a local minima. You compute the Hessian, which will be given in this S converge. Okay. So anyway, I'm not going into the detail of this. I'm skipping a lot of parts here, but my point here is that everything is explained. All of these things is explained with the same learning rule. And the main idea is to choose the approximation, the form of Q, and then you run Bayesian learning rule that becomes these algorithms, right? Different types of algorithm. And you can use this principle to derive all of these learning algorithms, right? So some people argue that what I'm talking about is variational inference. And I say to them that this is not. This is, of course, when you look at it, it looks like variational inference that you're trying to approximate a posterior. But the goal here is to actually derive different types of algorithms from different fields. So use this principle to see everything as the same, to see that every algorithm, not every, but most of the things that I talk about here, for example, they have the same idea that they're trying to do some kind of approximation to the posterior distribution, and this makes them what they are. So I don't want to call this variational inference because it limits it to, it asks me to stay in the territory of being an approximate inference guy rather than being a machine learning, general learning algorithm person. Okay. So I hope that I'm able to convey this to you, that I am encouraging you to think in this way that actually makes you, think more broadly. So there is related to that, there's a lot of work on variational inference. I've put some references here if you want to read about these. There are lots of methods that are entropy regularized, so they're putting entropy here. There are methods in reinforcement learning that are related to this kind of objective. In black box optimization, there's no entropy term, but that's also kind of related with this expectation using some kind of proposal distribution, so evolution strategy, Gaussian homotopy, smoothing based optimization, graduated optimization, stochastic search. There's lots of these things, and I've listed them here just for completeness. Okay. In approximate inference, people use call this natural gradient variational inference. I would encourage you to read the learning algorithm from Bayesian principle paper, where I have written how this is derived from there, and also how a mirror descent approach can be used to derive this Bayesian learning rule. Okay, so essentially all of it is like you use Fisher of the Q distribution as a preconditioner. It turns out that this step is actually related to Bregman divergence and mirror descent, and the theory is extremely, extremely beautiful. So it's all written in the section 2 of the paper, and you can read that. And this has a long history, and all starts in '99 from a person who was in Japan. He actually passed away 3 years ago. He used to work in Kyoto, and he actually had this idea of using this natural parameter and expectation parameters and writing these kind of updates. He was not writing exactly in the form that I presented here, and there's plenty of work that's done in between for us to kind of, in this paper, for us to get to a place where we are able to write these things down, and it's clarified a little bit further in this paper. And so there's a lot of history in this, and I'm not the only one who has been working on this. Now, these methods are related to what we call black box variational inference methods, but they're taking the gradient with respect to lambda, and we're taking the gradient with respect to mu. And this is a fundamental difference. So if you take lambda, you can't do any of the things that I talked about before. Okay, so it's very important that you do mu. And if you do mu, then here's a list of algorithms that you can derive from this. So I kind of talked about SGD, RMS prop, atom very quickly, then talked about least squares, gradient descent, Newton's method, Kalman filter. I just touched upon some of these. Laplace's method, stochastic variational inference, variational message passing. EM I didn't talk about, and there's other methods that are related to it. I just quickly touched upon this. But this paper has some of this written, others will be written at some point. So have a look at that paper. Okay, let's see the time. So we have about
a bit less than half an hour.
30.
So
Okay,
25 minutes.
Okay, so let's see what I can cover in that and try to very quickly go through this. So, I mean, this part is actually very, very simple, and it's kind of like just saying, how can we estimate uncertainty in deep learning? So in deep learning, we are always looking into, this example that we had is that you're just looking at one line, and I was saying you shouldn't look at one line, you should look at like many lines so that you get this variance out of it. And the question is, how can you get that, right? So this requires, so the principle tells you that if you want the variance, like the second order information, then you should do second order optimization. So you should compute Hessian or some type of it, but then that is expensive. But you can actually do some approximation and you can reduce the computations. That's what this part is about. The kind of uncertainty we are looking for is, is an example that's taken from this paper. This is actually, so this is what we call Bayesian deep learning, where we have, some task like image segmentation, and you want to segment this. And if you use a deep learning method, then it'll just kind of give you this answer and looks pretty good. But if you look closely, then you see that you've got like something's wrong. So here, like sidewalk is recognized as as road, which is very dangerous because your car could actually go into sidewalk. So you want to avoid this kind of confidence, and you can look into the variances. You can look into the uncertainty. So it's just the variance around your prediction. And if you do that, then you get this kind of confidence that shows you that you're not right at many of these places. So here you're overconfident, and also at the edges of objects you can't really tell which segment it belongs to, right? So having this kind of uncertainty helps you do that, right? So there is because the computation increases if you go anywhere beyond first order method, people have tried to just stick to SGD, which makes sense because it's quite expensive otherwise. But all of these methods, the main idea is just to, this loss example that I showed you, you were at an optimizer, you were perturbed slightly to get to know how the neighborhood looks like, and that gives you a variance estimate. So you could do this by injecting noise. So you could do this kind of dropout stuff, or you can look into SGD iterates, or you can look into the Hessian at the optimum. And these are just different ways to compute that variance. Right? So this is Bayesian deep learning. It scales well to large problem, but it's not flexible, right? Because you cannot go from a Gaussian distribution to a mixture of Gaussian and do some Bernoulli distribution and other things. So if you do variational inference and you derivate with respect to lambda, then you can do that. But the problem with this is that this doesn't really work. So the issue is that these methods, the mechanism of these methods, the algorithms are based on these deep learning, heuristics, the tricks of the trade that people have figured out how to make these things work. And if this algorithm looks very different from this algorithm, then the generalization performance is lost. So there were no papers showing good performance of variational inference on ImageNet scale, for example. And what we did in our work is that we try to show that if you see computing these approximation as kind of just a generalization of these kind of methods, then you don't have to change the algorithm much because they're pretty much the same algorithm. And then you can kind of keep all the tricks in place. You don't have to change them much. And then the method kind of does the right thing. So we set out to do this task on how to scale up variational inference to ImageNet. And basically, we wrote an algorithm called Vaughan, which is essentially what I showed you, this Newton type of method. And we did approximation to make it look like Adam, but then try to compute the variances from these scale vectors that you get in Adam. Okay, I'll give the detail soon a little bit more, but it sort of looks like this. So you have this problem. Blue is what Adam finds, and then red is what our algorithm finds. So in the beginning, they take very similar steps, but then our algorithm is giving this red line, which is the mean. And I hope you could see these pink lines here. These are basically other explanation of the data, which is not, that unreasonable. So you sample from the Gaussian, and the sample sort of spread out around. And this is showing you entropy of that. So it's telling you that you shouldn't only think that your solution lies only in this line, but rather there are other solutions around that are also good. Okay, so that's the benefit of this kind of approach. The code, if you go there, the code almost looks the same, but it makes two, three less modifications. So instead of putting this expectation inside, we just don't do it. We put the expectation outside. So this is RMS prop, and what we do here is that we have the same kind of gradient computation, computing the scale, but now what we're doing is we're sampling from a Gaussian. So we have this expectation, so we're adding back the one approximation that we put is taking this expectation inside, we're adding it back. Right? So we sample from a Gaussian, plug that in. Then instead of computing the square of the gradient, because second order information is important, we try to preserve some of this second order information. It's called Gauss-Newton approximation. So this Gauss-Newton is Gn there, and then we can sort of read the variances from the scale is what this shows. Okay, so few changes in the code. And you can go and you can download this code and you can sort of just replace one line. So you replace Adam by Vaughan and keep the hyperparameters mostly the same. You have to tune, there's two additional hyperparameters. You have to tune them for some time, but you can get it to sort of working you know, like this is an example where this segmentation, and this is the uncertainty of the segmentation. So you have lots of like places where you're uncertain at the boundary. It's the entropy of the class probability, essentially, telling you what you don't know. If you run this on ImageNet, so red line is our method. It essentially mimics what Adam does. And why? Because it's essentially Adam. It's just Adam with some perturbation. So we call this weight perturbed Adam. And we didn't have to change and tune it a lot, and that's why it kind of works well. Okay. So my point here is not that this algorithm is great. My point is that if you think of principles from top, see that Adam and the Bayesian learning rule, this Newton-like method, are very similar. So then you can sort of do minimal hacks to bring them to a place where you can keep some of the Bayesian properties, but still keep the simplicity of the deep learning. And that's basically what gives you this. So this is actually first of its kind. I don't know if other people have done it now, but at least a year ago, this was, this is 2020. So at least 6 months ago, it was the first method to do this. Unfortunately, as much as I would like to tell you that doing this will fix all of your problem, it doesn't. So many of these Bayesian deep learning methods, because they are still not getting close to, you know, doing better, more flexible posterior approximations, they're still very simplistic. So they don't actually do their job properly. Okay, so this paper is a very nice paper that talks about like how the Bayesian deep learning methods, they do not really know what they do not know. So they need to pay attention away from the data. They need to know not to be confident when the data has changed. So if you change the data, you do shift in the data, the method actually does not realize that it's going to perform worse and worse. Okay, so things don't really work well, but still, you know, you can try these tools, and there's Yarindal's tutorial that actually talks about all these things that I mean don't have time to talk about in this tutorial, but there's lots of code out there that you can try. What I would like to say is that this remains an open problem, and this is actually a very, very challenging problem. So if somebody comes to you and says that I know how to estimate uncertainty in deep learning, I would say you have to be very skeptical, because this uncertainty means a lot of things, and uncertainty means like roughly that what your model does not know. And you need to know that there's too many ways that your model may not know things, right? Because there's too many things out there that you have not seen yet. You have only seen some things, and most things in the world you have not seen. So you don't know most things in the world, and you want to quantify that using a method, and it's very, very hard, right? So technically, when you go into neural network case, you only converge to a local minima, and you perturb the solution at the local minima. So you look at these different lines that you can get. So, you know, the lines would vary in this range, but you still don't know what happens here. You haven't seen any data here. Should you be sure? Should you not be sure? The local minima is telling you that you should be very sure here, but should you be? And that's the question that you should think about, because where you don't have data, your model may be very confident, and maybe that's right, but maybe that's not. And this is a very, very tricky question. Right now, what we do is only a local uncertainty. We only know that if we fit this model and we look around the fit, then we know what we do not know, but this is only a small perturbation around the fit. What we need to know really far away from the data, but that's hard, right? And this is an open question, and I really talk about this as unknown unknowns. And if you don't know this term, you know, look it up. Things that you don't even know that exist that can come and hurt you, and those are the things that you'll be worried about. And we don't know how to get there. Okay, so there's a long way to get to this, and this is very simple fix. We talk about flexible approximation. And that's not going to solve the problem, because you see that if you need more complex posterior approximation, that means that your sufficient statistics have to be rich. It needs to go beyond quadratics. But if you need to go beyond quadratics, that means that you don't need to go beyond gradient in the Hessian. So you need to maybe go third order approximation, fourth order approximation, or maybe complicated sufficient statistics like mixture models. And this is going to be hard to fit. So how do you keep your methods simple as they are today, but still be able to estimate more complicated approximation? And that is not easy. Now, in the next part, I wanted to actually go and tell you a little bit about how one could solve this problem. So we have about row to go. Do we have 15 minutes? Are you there? I cannot hear you.
Yes. So we can have it. We will have the next session at noon. So there we have about 13 minutes left.
We have how many?
13 minutes left.
13. Okay. So I will try to get. So I will conclude maybe in the next session. Is that okay?
No problem. We can do that. So.
Okay. So let me just. So what essentially so next 5-6 minutes I'll just say very quickly. How do we solve this problem? And this problem is really important for lifelong learning. So what you know right now, it's a very subset of what you could see in the world in this time. But your life is long, and you're going to see a lot of things in the future. But you do not know about them. And if you know that you do not know about lots of things, then it's fine. Then as you learn them, you can update your belief. But if you're very, very sure that this is the truth, then it's very hard to change things. And this sort of appears in the deep learning setting, where you have lots of data at one place, and so you can learn everything about this. But then when you start like seeing more data in the future, you cannot like fix. You start looking at new data and you forget the old data, because now you don't have access to the old data. So this problem is called like catastrophic forgetting, and this paper, this review paper, is actually a very good paper to look at. But essentially what happens, like instead of doing this kind of learning, if you actually were learning sequentially, so you only saw dog and cat, and then you fit a network, and then you went and did lion and tiger, and then you updated your network to see this thing, and suppose you never see dog and cat again, eventually if you keep training like this, you'll forget about dog and cat. Okay? And this problem, it's called catastrophic forgetting of the past. If you don't see the data from the past, you forget it. This problem is related to not knowing. So you can see, like if you were in the Bayesian land and if you saw some data and then you saw another set of data, then you can use that posterior as the prior, and then you'll be fine. So everything is exact if you actually carry around your posterior distribution, like everything that you do not know. And here in this case, what you did not know is everything in this part. So it's actually saying that given that I fit straight lines, I should be very confident that there will be no data, but then I shouldn't be confident that there will be, I won't see any classes here, okay? So it, of course, depends on the data, but it gives, depend on the model, but it gives you a mechanism within the given category of the model to update your belief to what you didn't know before using this kind of Bayes rule. But you don't have the posterior distribution. It's going to be very, very hard to get it. So how do you solve this? So an alternate approach is to think about posterior approximation in the function space. Okay. So this is it's a hard concept to get to at first. So I'm just gonna like give you a very brief idea, and I'm gonna skip everything else, okay? So the main idea is that instead of approximating posterior distribution over the weights, let's look in the space of the predictor. So this is not neural network weights or parameters, but rather this is the data, right? So you have data, your neural network draws this line around the data. And essentially what you want when you don't want to forget is that when you get the second set of data, you want to fit a model such that it classifies this data well, but it also fits the previous data. Okay? But the issue is that your neural network weights, when you're training on this data, your neural network weights is to somehow make sure that it also is close to this line. And this line is not the weight. It's actually the output of the neural network. And you need to then fix like, where do you want this to be good? So you want it to be good here, 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 here. This becomes an infinite dimensional problem because the line is continuous. So this is a very difficult problem. And we call this function space regularization, and there are many names for this. Essentially the problem is that you want to change the neural network weights. So you want to get this line somehow that fits this data well and that matches this function or being somehow close to it. So how do you do this? So you want to do optimization in the function space essentially. That's the point. But this is very, very hard because the algorithms that you will get will be very expensive. So in this part, I wanted to show you that this kind of thing, it actually exists in a linear model already. And there is a tool called Gaussian process, this Bayesian technique, that actually here you optimize in the function space. And that has one-to-one correspondence with what happens in the linear in the parametric space. This idea can be used to approximate the posterior in the function space, and it seems like a more promising idea. Okay, I don't have time to go through this, so I'm just okay, wait a few more minutes. I'm just going to very quickly just give the idea for the linear case. What actually happens is, like, if you write the linear model and your weights are somehow Gaussian, suppose, then you can show that the function that you're drawing in the function space to classify the data, they are samples from a Gaussian process that has this kind of kernel. Okay. So what you do when you actually fit the data, so suppose you fit the data and you go from Gaussian to a multivariate Gaussian, but after fitting the data, so then you can show that this actually is this GP can be made, you could write it in closed form solution with the mean and the covariance. This goes through these data points now. So it's actually kind of telling you that you have these data points in the data space, and then you can directly write this prior or posterior over the function that takes this form, and it is closed form. And this only happens in the linear model. But what people have actually shown that neural networks, so if this was not linear and this was neural network, you can still do the same thing. Okay, so this is just the prior, so before observing the data, you could show that if you let the neural network width go to infinity, then this function is a sample from a GP. This kernel is a little bit more complicated now. It doesn't have closed form, but you can still write a program that will compute that kernel. Okay, so read that paper for that. And then the question is, like, can I do this on trained network? So, like, can I, like, write if I so I train a Gaussian in the weight space, does that induce a Gaussian process in the function space? And this is kind of an open question. And what we figured out in this paper, and I'm not going to go into the detail, that it does have this kind of closed form expression, and this is kind of Jacobian of your neural network, and this is the function output that you get, and you can read about it in this paper, but essentially there's lots of math here. Essentially what actually goes on is that these Bayesian learning rule that I talked about, this is the Newton method where you had this kind of moving average, that algorithm gives you a GP. So it's very powerful. The ideas that I talked about in first section, where you can write these Bayesian learning rule and you can show that they are similar, related to Adam and Newton's method. Essentially, the same algorithm gives you Gaussian process. Okay? I'm sorry I don't have time, but maybe tomorrow, if you ask me more questions, I can go into some parts of this. But essentially what we did is that we tried to show that this idea, is you can kind of, what you can do is you can take this binary classification problem, you can fit a network to it, then you can convert it into a Gaussian process because it gives you a GP, then use it to regularize the functions. Okay, and if you continue to do this, you can sort of avoid catastrophic forgetting. My computer is becoming very, very slow now. Hopefully it passes through. I was going to ask you a question, but I'll kind of okay. What? Maybe this is a good one. So what actually it tells you in the end is that when you write this kind of GP here, you can use that GP to show that some of the data points are more important than others. So intuitively, you know that the points that are close to the classifier should be more important, right? And if you plot these more important points, you see that they are kind of this borderline cases. So they're like outliers. They're the jokers of the world that don't fit the normal trend, and they're hard to classify. And these are like the ones that are far from the decision boundary are more regular. So your network, what it learns how to give importance to certain data points, and it says these data points are the ones that I care, and the others that don't look like this, I don't care about them. So you have a way of thinking about that in the function space. The other thing that you could do it's the same thing in CFAR. These are like more regular looking data points, and these are less regular looking data points. And this is all from writing neural network as Gaussian process, then trying to figure out what things are close to the boundary, what things are not. Okay, so I'm not going to talk about any of this, but essentially you can use this idea to do continual learning, to do active learning, and I don't have time to talk about this, but maybe we can discuss this tomorrow, and tomorrow we can look into this example maybe, and conclude with some open challenges. And I want to tell you some philosophy of, what do we know, what do we not know, and what do we need to know. So we'll conclude this tomorrow. We'll do a long question answer session. And if you have questions about these slides, we can discuss this tomorrow. But with this, I will sort of close this session. I'm done.
Perfect. Thank you very much, MT. So now we'll have your Wolf, so starting in about 2 minutes, and then we will continue with your session tomorrow, MT. And then we wish you a nice day, and let's continue. So this very interesting trip through deep learning and Bayesian methods.
All right. Thank you very much. Bye-bye. Have a good summer schooling.